Hi, my name is Beta Ameri. These are my partners, Christopher McGreevy, Alexander Vangarovsky, and Todd Schwarzman. We are a biomedical engineering team, and our project is geared towards helping the hearing impaired. Hearing loss is currently the most prevalent and fastest growing disability in the United States. It is also the #1 birth defect in children. We decided to do an experiment that'll improve the quality of life. The first part of our project was to do the first ever, actually the second ever, human clinical trial at Stevens. And the second part was to do a statistical analysis on the data we gathered from that human clinical trial. We used an EEG to analyze we used these sensors, this CleaveMed program, and that very laptop to analyze the signals produced in the human brain when a person is listening to music, a person is listening to speech, or listening to both at the same time.
Hello. Hi, my name is Kylie Rody. I'm a senior at Stevens. My major is civil engineering with concentration on structural. For my senior design project, I did the restoration of the Guggenheim Museum located on 5th Avenue between 88th and 89th Street. It's just a model showing the museum. So currently there is a restoration happening on the building where they stripped off the 12 layers of paint of the museum, which is a Frank Lloyd Wright building, because of the problem of cracking. They did laser scans of the building as shown, and all the red are the cracking which is existing right now. So my project explored the causes of the cracking, which I deemed to be the temperature differential as a minor cause, but basically the problem of wind loading was the major problem. So I studied and I made drawings from the original drawings of Frank Lloyd Wright. These were 1959 drawings that I obtained through the Paratus Group, which is the museum's representatives. And from these drawings, I could do some wind calculations on the building, and from there I saw that there wasn't sufficient reinforcement on the cantilevered walls. I'll show you a quick demonstration of what happened. These are the web walls and these are the cantilevered walls. And when the wind hits a building, it causes an ovaling effect. And with the ovaling, the cantilevered walls become deflected, which causes stresses in the concrete, which essentially cracks the building.
I'm here right now presenting our research on the investigation for the optimization of nanoparticle self-assemblies. The goal of this project was to create a nanoparticle assembly with a structure that resembled this shape right here. There are little spheres called nanoparticles that are about 100 nanometers in size. These particles are dispersed in a polymer matrix, and in order to create this shape, we use a microreactor assembly in order to promote the dispersion of silica in the matrix. Here are pictures of our results using beaker mixing, which is a batch process. And you can see that this is silica nanoparticles which have assembled together through dehydration of an emulsion. This picture right here is using two components, silica nanoparticles and a PVA polymer. You can see that the silica particles have assembled on the outside of the PVA core due to a desire to lower the chemical potential of the overall system. We were hoping that in using a microreactor we could control the process of self-assembly through a different mechanism, primarily kinetics. In this picture right here, we have the results of the microreactor system. You can see that the assembly is much more wrinkled in shape. This is due to the change in dehydration method. In beaker mixing, it was through heating. In the microreactor system, it's through the solubility of one phase in another.
So basically what we've done is we've maximized our aspect ratio. It's the ratio of the chord length to the wing length. The constraint in that is that you have to maintain some structural integrity as well, because the longer and wider that you make it, the more subject it is to forces at the joint as well as along the wing. but at the same time, you want to make it as large as possible because you want to get as much flow over the wing as possible to maximize your lift. Essentially what happens is if you don't do that, you lose a lot of flow to the sides. That's also why we have these things called Horner plates on the sides. They direct flow over the wings themselves. We have a few different control surfaces. These are the flaps. James will show you that they work. They will be put down.
The flaps control the rotational motion of the plane, banking left
the
or right. These are the ailerons. Another control surfaces is the flap. The flap is created to increase the amount of lift created by the wing. By turning it, we create a larger camber in the wing, and this increases the coefficient of lift, which then increases the amount of weight we can carry.
My name is Phil Kimball. I'm a graduate of Stevens, class of 1962. I'm a naval architect and spent my life building ships, but I'm here today at the Stevens Senior Design Project to see what the students have been working on. I'm currently the executive director of the Society of Naval Architects and Marine Engineers, and I work close by, so I thought it was a great opportunity to come over and meet some students and see what they're working on. Dan, you were telling me about the substrate and how you're going to be drilling through that.
Well, the tunnel is about 3 miles long, and it will go through a variety of materials, some very hard rock, some softer silt materials, and it requires more than one machine to do the work for the various phases of the project, one of which will be through the river, underneath the Hudson River, which is primarily through a silt material. This is a profile from the draft environmental impact.
How far below the surface are you going to be?
It varies. Obviously, the deepest part is through the Palisades, Jersey City Heights, a couple hundred feet at least below the street. And that's going, I think, primarily through diabase rock. We also gave a presentation for faculty at the end of last semester, and we did a presentation for the Tunnel Partnership, which consists of heads of New Jersey Transit, heads of the Port Authority
of New York and New Jersey.
Some of the companies that are involved in the preliminary design.
Good morning, everyone. This is Team Remy. My name is Jamie Tutt. This is Lily Abelana and Patrick Brosey. We're biomedical engineering majors for the class of 2007. And we've made an integrated PCA and IV pump, which you see here. Basically, this is an alternative to an epidural. We no longer have to relieve labor pains by placing a needle and medication into the spine. We're doing this because epidurals can cause several complications, which can be as minor as a severe headache or as severe as as paralysis, being that it is being placed near the spine and it's done solely by touch. There is no true way to figure out whether or not you're in the right place.
You know, part of the training is that it makes a motion, the fence reacts to that motion. It moves forward, it makes a thrust, let's say, so then the fence will back up.
This is our fencing training device, and the basic idea here is that there's training devices on the market for fencing today, but the problem is that they're stationary and they have no arm movement. So it's not a very realistic way for a fencer to practice the basic techniques that he needs to build upon in order to react adequately to an opponent's attacks or motions. And just as a football player practices getting into a three-point stance and getting out of it as quickly and with as much power as he can, a fencer needs to build basic techniques so that he reacts to motions on instinct and not having to think about whether his hand's in the right place or whether he's in proper distance to his opponent.
I was working in a chemical engineering group with Sarah Alphone, Jenny Hotomo, and Carolyn Butler. And together we worked on optimizing a carbon dioxide scrubbing unit used in anesthetic operations for a hospital setting. And over here is our system that we created. It consists of two hollow fiber membranes. The first hollow fiber membrane is used to absorb the carbon dioxide from a patient that breathes out into this inlet here. And the gas goes through the module, and the CO2 is filtered out into solution, and the clean gas comes out of here and goes back into the patient as a recycle. Now this module here contains a liquid membrane solution that's made of carbonic anhydrase, an enzyme that effectively catalyzes the reaction of carbon dioxide to H2CO3. And that the carbonate goes around in solution to a second module here, where it's picked up by a sweep gas that flows countercurrently to the solution. And the sweep gas strips the carbon dioxide from the solution, and it comes out of the waste stream here, which is basically air, and that's releases to the atmosphere. And this is a closed circuit solution for the liquid side membrane. And the idea is to reduce the volume of the inlet to outlet gas streams such that we could use a more expensive anesthetic agent such as xenon.
My name is Matthew Savari, and this is Team Spinal with the Spinal Triaxial Rotary Electro Goniometer. What this basically does is it measures spinal range of motion in 3 planes, X, Z, and theta, so that physical therapists can determine the efficacy of their therapy treatments from week to week, comparing different ranges of motion of the spine. This is Brian Testa, this is Faisal Sadom, and I'm Matthew Savari on Team Spinatrack.
What will some of the products and devices of the future be and look like? Some students at Stevens Institute of Technology have a few ideas. Sherry Carabin stopped by the 2007 Senior Design Expo to see what they've come up with.
From a future lunar rover to a new way to deliver pain medication to women in labor.
Instead of using an epidural, you can now use an intravenous drug. When you start to feel the pain, you can press the button and get a fast-acting pain management medicine that's going to be flushed into your system using the IV pump, which will increase its flow rate so that you can get all of the medicine flushed into you very quickly and relieve the pain almost instantaneously.
Those projects were on display at Hoboken Stevens Institute of Technology today as part of the 2007 Senior Design Expo. Throughout the year, seniors majoring in engineering worked on the potential products. Today, about 60 teams put their creations on display.
They bring the knowledge together from all their engineering courses in a project, and then as part of that also we try to have them develop other skill sets like teamwork. So as you see, we try to have some of these projects multidisciplinary, so they're learning some of the skills they'll need when they get out of here and get into the real world.
Some devices will be used to compete nationally. This suspension system will be featured in the Formula SAE competition.
This is basically designed to be a quick little go-kart with 4-wheel independent suspension. It's basically designed to go very quickly around a racetrack. It's designed to compete with other schools. The way it works is there's a pull rod which pulls the suspension up, allowing us to save a lot of weight and a lot of extra material.
This vertically articulating wheelchair is designed to give amputees or paraplegics more independence.
Oftentimes when an individual wants to enter a wheelchair from ground level, they create a rotational moment that makes the wheelchair fall on top of them and leaves them stranded. So what we did was we made a wheelchair that lets them enter from 9 inches above the ground and then helps them raise the seating surface to a regular height of 20 inches to allow them to use the chair more conveniently and with less assistance.
Opening those pill bottles can be difficult for just about anyone, especially seniors who might have gripping or other types of problems. This automatic pill bottle opener makes opening just about any type of bottle quick and easy. All you do is open the door, put the bottle inside, and press start.
The bottle opener would lower down and rotate the bottle and open the bottle, and then all the user would have to do is open it and take their pills.
If it were available on the market, students estimate it would cost about $75. Are you going to market it?
Well, we're, going to see how things go, depending on if we can patent it and all, and then we might take it a little bit further.
Indeed, former Stevens students have had their ideas make it in the marketplace in the past. This is Sherry Carabin, Neighborhood Journal, Hudson News Edition.
Thanks, Sherry.